Thank you so much. Thank you, Morteza. So thank you for attending another Zoom meeting, and thank you for having me in the Geography colloquium. To me, it's a real pleasure to be virtually back in Boulder as a professor now to share a glimpse of what was my PhD journey in the department. So I created a PowerPoint presentation to walk you through part of my dissertation work. And also I wanna share some background of how my project came to be. So the paper I'm presenting, titled White Spatial Politics in Alternative Food Activism in Argentina, is part of my dissertation on the linkages between the expansion of genetically modified soy cultivation for export, alternative food activism resisting the intensification of agribusiness, and migrant farmers from Bolivia immersed in a different agricultural sector, which is fresh vegetable cultivation for domestic consumption. So this is the larger project, larger context where my project takes place. In South America, Argentina is part of what Syngenta company has named the United Soybean Republic. That is an integrated network of soy cultivation, processing, storage, and distribution that extends across the borders of Argentina, Brazil, Uruguay, Paraguay, and Bolivia. The standardization of farming techniques in increasingly larger plots of land with the use of herbicide glyphosate has reduced the amount of workers needed to cultivate soy. Activists and scholars denouncing the socio-environmental impacts of the soy complex refer to this model as agriculture without farmers. The yellow dot in the central plains of Argentina is where I conducted most of my fieldwork, and it's also the place where I am from. Río Cuarto is a town of 200,000 inhabitants, and it's an important agricultural hub in the country. So in 2013, I was an active member of local activist organization Río Cuarto Without Agrotoxins, denouncing pesticide drift over the city from surrounding soy fields. Here you can see this is mostly soy and corn fields. Here we were in downtown Río Cuarto, handing out flyers to inform people about the impact of glyphosate, and we were collecting signatures to raise support for a municipal ordinance project to transition to agroecological production in the city. The project was a 7-year plan to reduce toxicity of agrochemicals in municipal lands to promote the local production of food without agrochemicals. We were following the principles of food sovereignty as stated by international peasant movement, La Villa Campesina, that established that people and not corporations should control localized food systems. So in 2014, I moved to Boulder to start my PhD, and I had to define my field for history and theory of geography. So preparing for this talk, I went back to my history and theory folder, and I found this slide that I copied from the presentation I gave to the class at the time. So it's fun to me to see my own thinking process. And so I define my field as political ecology of food sovereignty. And I identify these 3 lines of thinking, subfields: Marxist critique of political economy, knowledge production, circulation, and application, and post-humanist approaches to the nature-culture binary. So I had all these questions in mind. How is capitalism enhancing even further commodification of nature? Who pays the costs of externalization of nature in capitalist economies? What knowledge is being elevated at the level of truth in food sovereignty movements? How does food sovereignty knowledge get translated by state programs and social movements? And what do we gain by decentering humans as these central actors? Is nature separated from culture? Should we strive to reconcile them? So with all these ideas in mind, I went back to Argentina in 2015 to conduct my preliminary research. And this is when my project really started taking shape. While soy continued to be cultivated and exported, herbicides continued drifting over the city, and activists were still pushing for agroecological production, I wonder who is producing the food we purchase at the store and we eat while all this is happening. This is when I shifted my attention to these farms surrounding the city, where migrant farmers from Bolivia live and work to cultivate the produce consumed locally. Each of these red polygons, is a farm typically owned by Argentines and worked by Bolivian families working as sharecroppers. Vegetables are cultivated in open rows, in open fields, and also in greenhouses, with the use of many different agrochemicals, including herbicides, insecticides, and fungicides. Surrounding Rio Cuarto, there are 33 farms that produce an annual volume of vegetables enough to feed 300,000 people. That is the entire city and 4 smaller towns in the area. All the produce is transported to a centralizing market where grocers and distributors buy wholesale produce and farmers go back to their farms outside of the city. The puzzling thing to me was that the agroecology transition project we were raising public support for, there was no mentioning of these issues. It was not a topic of discussion who was working in these farms. So that summer, when I started asking about this, I got a simple answer. And the answer was, they use agrochemicals and therefore are not part of the agroecology project. Rio Cuarto is not unique in this regard. In every major city around the country, including Buenos Aires, Mendoza, and Cordoba, fresh vegetable cultivation is done by farmers of Bolivian origin. This map to the left shows the presence of Bolivian farmers at the county level, information that I gathered from secondary data. The actual amount of Bolivian workers in Argentina is largely unknown, as many of them don't have work permits and therefore are not registered. There is a long history of racialization of this workforce in Argentina. Starting in the mid-19th century, when Bolivian farm workers were employed in sugar and tobacco plantations in the Argentine north, this migrant group was constructed as the lowest strata in racial and labor hierarchies in the country. Now, fresh vegetable production in Argentina is signed by precarious working conditions, lack of price regulations in centralizing markets, with several layers of brokers that profit from Bolivian labor. Bolivian farmers live and work in peri-urban farms where they are directly exposed to a broad range of pesticides on top of pesticides drifting from soil fields. So in this paper, I argue that agroecology activists reproduce white spatial politics by further marginalizing migrant farmers on the basis of their chemically intensive practices. So following with the sequence of events, in 2017, I came up with a good enough research question. Thank you, Joe, for all that feedback. And I spent a year doing interviews, participant observation, focus groups, and farm surveys. And I engaged with a broad range of actors, including activists, Bolivian farmers, agribusiness actors, agronomists, and officials working at different institutions pertaining agriculture. In this paper, I focus on the interviews and participant observation with agroecology activists. So the narrative of agroecology activists I interviewed begins in the early 2000s when glyphosate drifting from soil fields started to become perceptible in people's bodies. Mostly urban, white, formally educated professionals and medical doctors in different towns in soy-producing regions organized to collect medical diagnosis of people living in proximity to soy fields and created maps of cancer and other diseases associated with glyphosate. Different groups coalesced under the network of fumigated towns, connecting the dots of socio-environmental violence inherent to the soy complex. The body of Fabian Tomasi, an ex-farm worker who used to pump herbicides into crop dusters, became the symbol of the struggle against soy agribusiness in Argentina. Glyphosate affected his central nervous system, and he died in October 2018. The figure of his white, deformed body clings to the mind of millions of Argentines concerned with pesticide drift. As a result of the efforts of the network of fumigated towns, around 400 municipalities in soy-producing regions declared free agrochemical zones around urban centers, varying from 1,500 to 300 meters from city limits. In these buffer zones is where pesticide drift activists push for agroecological transitions to supply cities with local products without agrochemicals. This is one of the few agroecological farms operating in Río Cuarto, and this one in particular is the model for the transition project. You can see its circular design where different varieties of vegetables are intercropped in concentric circles, optimizing the use of nutrients and soil cover. 2 people work this farm, the owner of the land and 1 employee. They produce vegetables enough to feed 30 families year-round. By contrast to the circular farm, here you can see the long, homogeneous, and densely cultivated beds in the farms worked by Bolivians. In this farm, there are 3 families living in these 3 houses up here, working as sharecroppers for an Argentine farm manager. Here you can see, I took these pictures at an agroecology workshop that I participated, and it took place in this circular farm that was organized by activists and agronomists. And they were teaching mostly agronomy and biology students and people from the general public how to make organic fertilizers with simple materials. Here we are touching and smelling this healthy biodynamic fertilizer to enhance plant growth. By contrast, again, these are the practices that take place in the farms worked by Bolivians, the back-breaking labor of harvesting, and also the spraying of highly toxic chemicals, including gas methyl bromide, in greenhouses. This image was produced by the local activist group I was working for, and then I was studying in 2017. And it was part of a social media campaign to raise public support for the agroecology transition project. The picture indicates that there are more than 25 different pesticides in the fruits and vegetables consumed by Argentines, as reported by the National Bureau on Agri-Food Quality in 2016. Activists request and compel others to demand food without pesticides, as if it is poisoned, it is not food. The work that this framing does is to link widespread anxieties around pesticide drift from soy fields with consumers' concerns over contamination of food, erasing altogether issues around farming labor and unequal exposure to toxicity. This other image, created by Río Cuarto without agrotoxins, is a clear example of what I mean by white spatial politics. This is a map of the agroecology transition project. The yellow polygon surrounding the city indicates the proposed area where agroecological production should take place, protected from pesticide drift. The blue line towards the outside delineates the buffer zone, the chemical-free zone, where fumigation with glyphosate is forbidden. The red polygons towards the outside are the farms where Bolivian farmers live and work. And as you can see, these farms are mostly unknowingly left outside. So this map speaks to agroecology in this particular place as a project of spatial reappropriation, where some people are protected from pesticide drift and others are left outside of the protective shield. So in my paper, I discuss how is this map possible? How this exclusionary project came to be as a tool for socio-environmental transformation. So these questions led me to delve deeply into the meanings and workings of whiteness in Argentina. Scholars working on this topic define whiteness in Argentina as an ethnic racial identity formation that is seen as neutral and normative for those who inhabit it, and thus contributes to perpetuate white privilege. Whiteness in Argentina, or blancura, is the country's most persistent, albeit fragile, foundational myth. In my paper, I discuss the history behind whiteness in Argentina, starting with state-led projects to populate the country with European migrants. So I analyze specifically what are the workings of whiteness, how I see whiteness at play in agroecology activist work. And I identified 3 different reinforcing mechanisms. On the one hand, there is an emphasis on technical and legal aspects of agroecology and pesticide drift to foster the creation of chemical-free buffer zones. So there is a whole discussion about different toxicity levels and different regulations about these chemicals. Then there is a consumer-centered activism that appeals to middle-class anxieties around agrochemical contamination of fruits and vegetables, linking anxieties around agrochemicals drifting from soy fields and residues of pesticides in the fruits and vegetables consumed on a daily basis. And finally, activists put forward claims over constitutional rights for chemical-free environments that exclude migrant workers based on their citizenship status. So as a result of these reinforcing mechanisms, a double food standard, a double food system for production, distribution, and consumption of food is on the rise. Agroecological products for those who have access to these networks and also have the economic resources to purchase these products, and cheaper vegetables with pesticides residues for the majority of the population. And to end my presentation on a positive note, since December 2019, with the return to power of the leftist party in Argentina, there are new policies in place to support small farmers. Now, in the province of Buenos Aires, Bolivian farm workers are organizing themselves to put in agroecological colonies as a way to reclaim access to land and fair prices for their products. What it remains to be seen is if these white urban agroecology activists I was talking about will join these efforts or will remain separate. And this is something I continue investigating and getting ready to go back to Argentina when possible and delve into this issue and see what are these policies and how are these colonies operating and how agroecology activists are connecting or not with this new phenomenon. And that's the end of my presentation. Thank you so much, and I would love to answer any questions you may have.
Thank you so very much, Daniela. Really interesting talk. There's a 20-second lag on YouTube. So before questions come in, I want to make a comment. Folks, there's another talk coming up by Tasha Snow. Today's an unusual colloquium. And if you have questions, please post it in the chat box. I'll read it off to Daniela. We have time for questions. Thanks so much, Daniela, for sticking to the time limit. I have a question for starters, and it really doesn't speak to the core of your work, but I was wondering if you happen to know at all about the sampling strategies for measuring pesticide use in agricultural lands, just out of curiosity and how it's measured.
What strategies?
Sampling, as in how is it measured, sensors, or how are those maps generated? You know, I've done some soil mapping, so it's mostly out of personal interest and how the sampling might affect the results that we see.
Yeah, should I answer now or wait for
Yes,
later?
please go ahead.
So the sampling is done at decentralizing markets by markets officials. And so every Monday, there is a whole protocol. They randomly select producers, and they sample 10 different varieties of vegetables. And then this is tricky because the laboratories are only in Buenos Aires. So all the samples from all over the country are shipped to this laboratory. And always the results are made available after the produce was sold. So I argue in my work that there's a whole bureaucratic procedure. The reason why farmers need to bring their produce to the market is to guarantee the sanitary quality, but the results are not made available on time. So it's a very tricky process. And also the infrastructure and the funding for doing these very expensive analyses are minimum. And so we don't really know. There is a protocol, but the results and the way in which it's done is not really guaranteeing public health. There's a whole bureaucratic procedure through which farmers are brought to the market. I don't know if that answers your question.
No, it perfectly did, actually. I think I was a little tipped off when I saw the map. Now I understand how things are measured, but certainly interesting, and I think that does take out a lot of bias from some aspects. Thanks again. I don't see questions from the chat. I know folks will take your time to post it, and there's another talk. So I suggest we move on to the second talk, but if you don't mind, stay on, and maybe there's a little bit of time for Q&A after Tasha's talk too. So thanks again. And with that, I want to introduce Tasha Snow, PhD candidate here at CU Boulder Department of Geography and CIRA's Cooperative Institute for Research in Environmental Sciences. The title of her talk is "The Heat is On: Investigating New Applications for Satellite-Based Sea Surface Temperature in glacier-ocean systems." So Tasha, if you could share your screen.
Can I?
Yeah, I think Daniela needs to stop the share so that we can switch. Sure. I believe. No worries. Thank you. Okay. Perfect.
All right. You can see just the slide. Perfect.
Yes.
Good. Yeah, welcome everyone. Good afternoon. Thanks for joining. I don't know some of you, I know because I've been hiding out in series the past couple years, and especially before, no one's seen anyone since the pandemic. So it seems like I haven't seen anyone for a really long time. My advisors are Walid Abdelati and Ted Scambos as a research scientist at Ceres. Today, I'll be sharing with you some of my work from my dissertation that, as Morteza said, I'll be defending next week. But this isn't the entire thing, so it's not entirely a spoiler if you are planning to come to that. The work that I'm doing is expanding how we can use satellites to study glacier-ocean systems. So to start off, this on the left is a sketch of an ice sheet or a glacier, and on the right is the ocean. And I'm interested in how they interact with each other. And specifically how we can use satellites to study how they interact with each other and how the oceans have changed through time. So to start you out, I'm gonna first give you a little bit of history on our understanding of the ice sheets and the ocean's role in their change. So that all began, the study of the ice sheets began with Landsat being shot into space by NASA in 1972. And that was our first glimpse of what an entire ice sheet is. So this was our first Earth science satellite. You can see across the top, there have been 8 of them since, and Landsat 9 is being shot into space next year. The lines show how long those instruments were giving us imagery from space. And you can see Landsat 6 is a little blip because it failed on launch and didn't reach orbit. So that was a dud. But we've gotten a lot of amazing imagery of the satellite or of the ice sheets since that Landsat program began. But the NASA Earth Science program has an entire fleet of satellites, and many of them give us data about the ice sheets. I'll be specifically talking about the Terra and Aqua satellites, an instrument from that. And as I just pointed out, there's Landsat 7, Landsat 8. I'll breeze over some of the data that I've used from that. But yeah, these instruments are providing us a lot of information now about the ice sheets. Now, you may be wondering, what is an ice sheet anyways? So I want to make sure I give you some of that background. So an ice sheet is a continent-sized piece of ice, pretty much. This is the Greenland ice sheet. There's one in Antarctica. And the ice sheets are really important to the globe because of their role in climate change, both from sea level, they affect our weather, especially here in Colorado. And the Greenland ice sheet specifically contributes 1/4 of total sea level rise each year. Now, zooming in on what the ice sheet looks like down on the ground, this is a bird's eye view from an airplane of what the edge of the ice sheet looks like. And to think about it, looking at it was like when you pour waffle batter into a waffle iron and you watch it kind of ooze into the nooks and crannies of the waffle iron. That's what the edge of the ice sheet is, where you have these outlet glaciers, are ice streaming out from the ice sheet in through valleys around the edge of the ice sheet around Greenland. And you can actually see these streams because of the crevassing that happens. This is the back end of an outlet glacier as it goes back into the ice sheet. So it's flowing out in this direction and just kind of oozing out of the middle of the ice sheet. And some of these are land terminating, they end on land, and some of them are marine terminating. But this is kind of the scale of what we're looking at. This is Mike McFerrin. He's a graduate from the geography department a year ago, maybe a couple years ago. It's hard to keep track of time anymore. But this is kind of the scale. This is actually a smaller glacier in Greenland, so they're huge. And they're marked, these outlet glaciers are marked by the relatively fast moving ice that comprises them, which is shown in the blues and purples here. And they account for over half of the ice mass loss that's occurring in the Greenland ice sheet, and almost 100% of the ice loss in Antarctica. So they're super important, and that's where I'll be focusing some of my work. And a lot of these velocities, just for reference to the satellites we saw a moment ago, these are created using radar and optical imagery that track features, so you can measure how fast these are moving. So kind of a historical context for what we saw is that in the late 1990s is when we began to see change. This work was done by Waleed, and it shows, it's kind of got an outline of the Greenland ice sheet there, and each of these are outlet glaciers. And the glacier thinning is shown in red, and thickening is in blue. And what they found is that outlet glacier thinning was dominating lower elevations, and there was lots of change happening. Then moving over to Western Greenland, focusing in on that area, there was a huge glacier, the fastest moving glacier in the world, Jakobshavn, that began to experience rapid thinning and rapid retreat in 1997. So just kind of for context, so this is a satellite image looking down on the glacier. You can see the streaming again of the ice on both sides where this glacier is, and this is the calving front. where ice chunks break off into icebergs. Melange is the floating icebergs and broken sea ice that's floating on the ocean. So this is the fjord, and then they flow out to the open ocean. And this shows the calving front as it's moved back through time. The calving front for Jakobshavn has moved back about 30 kilometers over 100 years until about 1964, and was relatively stagnant. And then all of a sudden in 1997, it began to retreat. And they've seen almost 20 kilometers of retreat since then over the next decade. And yeah, and so that glacier began to change rapidly. And then a few years later, Helheim Glacier and Kingrid-Lutzwak Glacier on the southeastern side of Greenland began to also retreat. And because all of these were kind of going at once at similar times, it was hypothesized that there must be a common link or trigger for these retreats. And usually a common trigger might be air temperature, or it might be ocean temperature, like an ocean warming. And it was hypothesized that this was due to ocean warming. But the problem is there were no instruments around Greenland during these time periods for the most part. And so we had no idea what the ocean was actually doing. It wasn't until 2008 in this study by David Holland and others, where they gathered together ocean temperature data from fishing trawlers, which is a remarkable data set to put together. And they showed that this is an image of the western side of Greenland, and Jakobshavn is right over here in Disco Bay. What you'll notice is as we move towards 1997, you see warm water creeping up the western side of Greenland. And in 1997 is when it reached Disco Bay and began affecting Jakobshavn. So this was our first evidence that it was ocean warming that triggered this glacier to retreat. And that ocean warming is really important for this. So that's a lot of ice that Jakobshavn lost. Now, focusing in on what these systems actually look like and why warm water is important. Here's kind of a schematic of what the ocean looks like. You have warm water at depth, and that's counterintuitive, but this happens because the warm water is relatively salty, and so it's more dense. And then on top, at the surface, you have polar water that is derived from the Arctic, and ice melt from the glacier and ice melt from sea ice. All of that creates a relatively fresh water mass that sits kind of at the surface. So that's kind of the dynamic of the water that you have there. And in both Greenland and Antarctica, you have two different kinds of circulation that are kind of dominant. Specifically in the fjord, in Greenland, you have glacier-driven circulation where that deep warm water comes into the grounding line where the glacier last meets the ground. It melts the glacier, that fresh water mixes into the surface and makes a plume that's buoyant and rises to the surface. And then it exits away from the front of the glacier and that continually draws more heat in at depth. The other kind of circulation that happens, this one is dominant during the melt season in summer because that melt is creating that circulation. The other kind that we have is wind-driven circulation. That's also called intermediary circulation. And what that is when you have the winds pumping, they'll drive water out at the surface and in at depth, and then in the opposite direction as the winds shift directions. This one's really important because it can pump about an order of magnitude more water into the fjord, into the glacier face than the other can. So it can pump an entire fjord, kilometers worth of water in a matter of a few days. So this one's really important, but it's oscillatory. So it changes over time. And that I'll be talking about a little bit later in my second chapter. But yeah, so kind of overview of why I'm doing the work that I'm doing is because there's relatively few ocean records around Greenland and Antarctica, as I mentioned. So the question is, how can we use satellite records to fill in those gaps? Because a lot of those records began in 2008 or 2010. And as I mentioned before, all of these glaciers began to change in the early 2000s and 1990s. So how do we know what the ocean was doing during that time? And we had satellites up all the way back to 2000, some back to the 70s, as I mentioned. So yeah, my work is focused on expanding our understanding of the ocean using satellite-derived imagery, specifically sea surface temperatures. So getting into my first project, or the main project that I'll be talking to you about today, was to expand our understanding of what they can actually tell us. Sea surface temperatures tell us about, measure the skin of the ocean. And so can they tell us about surface water temperatures? Can they tell us about deeper water temperatures? And that's what I was investigating. I am doing a case study at Helheim Glacier, which I showed before. This is a picture of Helheim Glacier on the left, and a lot of crevassing. It's moving out towards the right. And there's that melange that's all floating chunks of ice. And you can see a plume here. That's that glacier-driven circulation that I talked about earlier. And for context, this is what the front of Helheim Glacier looks like. So it's about the same height as Confluence Tower in Denver. It's about 30 stories tall, so it's pretty massive. One other thing to point out here is that you can see a bathtub ring kind of around the edge of Helheim Glacier. That's how thick the glacier used to be. So it's undergone a lot of thinning and retreat recently. So I'm interested in sea surface temperatures, and one helpful thing about this area is that there have been a few studies that have used sea surface temperatures in the area. But overall around Greenland and Antarctica, there's been very little use of sea surface temperatures. They could be useful for complementing the field measurements, but we don't really know. There has been conflicting results on how useful they are. In this study, on the left-hand side, Ian Howitt and others found that offshore sea surface temperatures were warm during the time period when Helheim Glacier began to retreat, so there was likely an ocean trigger there. But a few years later, another study came out by David Sutherland and others that said that sea surface temperatures don't correlate with temperatures below 250 meters, which, if you remember, below 150 to 250 meters is where that warm water is stored. And so we aren't really measuring how much heat is actually getting to the glacier if we can't get at that deep water. So I'm exploring what we can actually do with these sea surface temperatures and trying to resolve this question. And one thing I want to point out is that these two studies were done in summertime using summertime sea surface temperatures. And I'll point out in a moment why that's important and why that makes these not as useful for really understanding what sea surface temperatures can tell us. So just an overview, the two water masses in front of Helheim Glacier are called polar water, that's that cold water, and Atlantic water at depth. That's what brings the heat to the glacier. And I'm using 3 data sets in the work that I did. I'm using moored ocean temperatures. A mooring is an instrument that sits at specific depths and measures a time series over a few years of the temperature and salinity in a specific location. And I'm using a mooring from 290 meters inside that warm Atlantic water to compare to sea surface temperatures. And I'm using MODIS, which is an instrument on board the Aqua and Terra satellites that I pointed out to you earlier. And for MODIS, there is a daytime and a nighttime sea surface temperature product. So there's actually 4 products that I can use for this. And then for comparison, I'm also using ERA5 reanalysis data, which is the air temperatures that I'll use to compare to. And I'm using air temperatures and ocean temperatures because sea surface temperatures are kind of at that continuum between the atmosphere and the ocean, and it's getting heat from both sides. So that's why I want to know which one is reflecting more. All right, so what do sea surface temperatures potentially measure? So when I talk about sea surface temperatures, I'm talking about a sea surface temperature skin measurement. So this is what we're actually measuring. So the surface that's slightly cooler than what the actual water column is. Then there's 2 dimensions to what sea surface temperatures would actually be measuring because of how the water column changes throughout the year. There's a wintertime upper ocean temperature. So we have depth here along the y-axis and temperature increasing to the right. And in wintertime, basically from surface down to whatever depth. The water column is pretty homogeneous. So what you measure at the surface is also what is the temperature of the upper ocean down below it. In summertime, a surface thermocline is created, and that's because you have the sun coming up, you have polar summer, there's less winds in summertime, and so there's less mixing of the surface. And this thermocline is a steep gradient in temperature. And once that forms, the temperature that you get up here is not going to be reflective of anything below that thermocline. So that's really important. Now, beyond the seasonal differences in the upper ocean, you also have a diurnal difference. And that's between, you have the diurnal thermocline that is created during the daytime when the sun comes up and is warming the surface. There's less winds during the daytime than at nighttime. And so a sea surface temperature from during the day reflects a very different temperature than what is probably down at depth. Just in case the question popped into your mind, what happened to the warm water in this? This is temperatures down to 10 meters, and that warm water is 250 meters down below. So we're just talking about the very upper ocean here. But yeah, moving forward, the difference between night and day is really important because I talked about those daytime and nighttime products in MODIS. And so what I kind of showed in the research that I did is that this daytime and nighttime product is really important. MODIS takes 12 to 18 scans per day of an area, and those are binned into daytime and nighttime based on whether the sun is up. But as many of you might realize, the polar regions experience polar winter and polar summer. So the daytime product will be taking about 18 scans per day, whereas the nighttime product in summer will only have 1 or 2 scans per day potentially. And the opposite for wintertime. So if you were to take an average across, a year in the daytime product, you're gonna get an average that's skewed towards summertime and vice versa for wintertime. So that's really, really important because all of those studies have been using a summertime measurement when you have that diurnal thermocline, and they're using daytime products. But what I'll show in a minute is that as we expect from that schematic is that the wintertime products or the wintertime measurements are actually reflective of upper ocean temperatures and not the daytime summer measurements. So that's really important going forward. I'll come back to that in just a minute. All right, so just scoping in on Helheim Glacier, the general circulation around the area is that you have Atlantic water off the coast coming up through the Erminger Current, and it sits off the continental break just outside, and it's Atlantic water from surface down to depths beyond what we care about right now. And then there's the East Greenland coastal current I'll also talk to you about, which is composed of that polar water, relatively fresh. It sits at the surface, and below that is Atlantic water. Zooming in on Helheim, this is an image of showing the Erminger Current as well as the East Greenland coastal current again. And then this is the bathymetry. So what it's showing you here are these troughs that cut into the continental shelf. And what you might notice is this is sea surface temperature averages for the area, is that there's warmer sea surface temperatures along those troughs, which is really cool that you can see where these deep bathymetric troughs are because water is diverted from the Erminger Current from surface down to depth onto the continental shelf. And so that area is really interesting to study. I'm going to show you some averages from there and also the East Greenland coastal current where you have averages from the polar water and Atlantic water from the Erminger Current. And I'll be comparing it to a mooring that measures ocean temperatures near the coast where that water is flowing into the fjord.
Tasha, this is Morteza. If it were up to me, I would like for this to continue forever. This is really interesting, but may I ask that you wrap up in about 5 minutes?
Yes.
Thank
Definitely.
you.
All right, so here are the records from each of those locations, just so you can see what they look like. And my interest is in how much of the variability in each of these records is attributable to the upper ocean and how much is attributable to air-sea interactions, so air temperature. And so what I've done is I compared first sea surface temperatures from that shelf trough box. That's an area where the water is diverted towards Helheim and towards Thermalik Fjord. What it shows is that in summertime, there's pretty close relationship between air temperatures and sea surface temperatures. So this is through time and temperature here on the y-axis. But you can see here that they're very different during wintertime. And we can see this in a linear relationship between air temperature and sea surface temperatures here in summer, but not in winter. But if we compare to the mooring down in that Atlantic water, the sea surface temperatures reflect that mooring in wintertime, but not in summertime, which makes sense. So you don't have a linear relationship in summertime that's very significant, but you do in wintertime. And this is because you have a lot more mixing and winds, kind of coupling the sea surface to what's happening at depth in that water column in wintertime. So I really want to get a continuous record from sea surface temperatures of that deep water. So what I do is I take out the relationship between air temperature and sea surface temperatures, and I adjust the sea surface temperatures to create this record here in orange. And what that ends up doing is creating, we see a linear relationship between sea surface temperatures and that mooring record, almost a one-to-one relationship. So I've produced a way of estimating deep water temperatures in this area. And the reason why we can do this is because sea surface temperatures in this area, as I mentioned, measure an area where that water is diverting onto the continental shelf and mixing. And it's continuing on at depth to where that mooring is. And so it's pretty much a homogeneous water column. And even though there's 80 kilometers difference between those two locations, it's a good estimator for that water that's getting in towards Helheim Glacier. Now I also take that East Greenland coastal current box to look at polar water, and that only reflects the surface. And here the Atlantic water, where the Erminger current box is taken, that reflects deeper temperatures. And this is the record over time that I've produced. And what I'm showing is monthly averages with a filtered 100-day Butterworth filter to show what the records look like overall. And there's two things that you can take away from this. First, one thing that you'll notice is that shelf trough area isn't similar to the Erminger current in all months, or more similar to the East Greenland coastal current. There are some periods where it's closer to one than the other. And what that tells us is that this water is diluting. It has variable dilution as it crosses the continental shelf. And this actually relates to how wide the East Greenland coastal current is. That regulates how much it's diluted. The other thing to notice here is that in the early 2000s, there's pretty warm water in all three areas. And that's actually when Helheim Glacier began to thin. So this is giving evidence that there is, that the glacier began to retreat because of warmer water being in that area. So for a summary of this, I found a new sea surface temperature processing method that provides estimates for upper ocean temperatures. There's this adjusted shelf sea surface temperature that provides a proxy for deep water temperatures as well, and that offshore temperatures did not predict inshore Atlantic water temperatures because there's variability in how much it's diluted. So you can't look at temperatures offshore like some people have and estimate what the temperatures are near the glaciers. And then there's this deep water temperature variability that seems to have correlated with Helheim retreat. Now, there's just a brief summary that I was going to give of a few other studies, but some of the work that I did in Antarctica. But overall, what I wanted the take-home message to be here is that there's, as you can see here from the scale of this, there's a lot of ice in both Greenland and Antarctica, and we know that it's melting. These ice sheets are important players in climate change, and it's crucial for us to understand what's driving their variability. And there are huge gaps in our understanding of the role that the ocean has played, even though its role is significant. So now with the work that I've done, sea surface temperatures can provide us with a new way of determining ocean temperatures in times and places that we didn't have any field measurements. Expanding their use elsewhere, sea surface temperatures will hopefully help us to tease out the triggers for glacier retreat and hopefully help us to predict how they'll change in the future. So I wanted to just acknowledge my advisors, committee, and collaborators, and also to my funding sources. So thank you. I'll take any questions.
Thank you, Tasha. This is fascinating. I'll wait for a couple of minutes for folks to post their questions in chat. Before I get there, do you want to tell folks what time your defense is? If it's open to public, maybe they can tune in.
Yeah, my defense is at 2 o'clock Mountain Time on Friday.
All right.
I don't have a Zoom link, but if you're interested, you can email me and I'll make sure that you are included on that.
All right. One person interested right here. So I'll get a link from you. Okay. Lots of claps in the chat. There's one question that talks about salinity. Can you track the warm plume by salinity? And I believe it refers back to the deep warm waters, if I'm not mistaken. I think that's what the question was posted.
So at the surface, a lot of that warm water that's brought to the surface in those plumes is actually a little bit more fresh. Salinity, you can. I haven't worked on using salinity with satellite imagery, and you can do that. You can infer salinity. The temperatures, what I was mostly focused on, you can track these water masses using salinity, yes. Primarily the heat can change as it advex towards the glacier though. So I was primarily focused on heat here. In one of my other studies, I'm focused on salinity as well, to be able to track currents and things like that using this.
Great. And again, I do want to invite folks to, because this was only an abridged version and there was more to present, to attend Tasha's talk. One question that I had was when looking at seasonal differences and then the diurnal part, are those seasonal averages over 20, 30 years that we were looking at, and the relationship of temperature and depth? Just wondering how the seasonality of what's overall taken out of that, if at all.
So the seasonal differences I showed were just kind of schematics. There is some variability from season to season, and I kind of account for that with the air temperatures. Yes. Which section were you particularly?
I think that question was raised in my head when you were both showing the schematic diagram of the log of depth, as well as the one that you were showing the mixed effects. But again, it was mostly out of curiosity for viewers. We were trying to write a proposal with Tasha, and these questions were in my head at the same time too.
Yeah, I mean, so it really depends on the winds a lot. So if you have a year that's exceptionally high winds, this will be less of an issue. But yeah, in general, as you saw from that comparison between sea surface temperatures and sea surface temperatures and air temperature, in general, it couples pretty well in summertime. But yeah, you do get some of that interannual variability by getting rid of the air temperature signal. Does that answer your question? Yeah,
exactly. No, I was just looking at the sea surface temperature. I think that is really helpful. And I am checking. I don't see. I hope Lynn's question is answered. I don't see other questions for this talk. So thank you again for this wonderful talk. I want to go back to Daniela's talk. There was one question from Milen. I'm sorry if I'm mispronouncing your name. How specific is this problem to Argentina? Do you have a sense of where else similar dynamics are at play, and what strategies have been found to deal with them, if any?
Thank you, Tasha. That was awesome to learn about your work. And you you'll rock next week. Yeah. Thank you, Milen. Hi, Milen. Yes, I just saw your question. I was thinking about the answer. And no, this is not unique to Argentina. We see white privilege normalizing access to healthy food for some people, and also normalizing the fact that there is a migrant labor force that is doing the harvesting work. Here in Michigan, for example, I'm talking to people asking, there's a huge fruit industry. And it's common knowledge that there are migrant farmers that come every year for harvesting blueberries, apples, peaches. And so that is not unique to Argentina. What I would say is unique to the Argentine case is the way in which the agroecology pesticide drift activism came to be as a response to this massive soy complex and the use of glyphosate. And so starting from there, this pesticide drift activism became, people know about the impacts, the health impacts and the environmental impact of glyphosate. And then what happened was this linking that pesticide drift from soy to the presence of residues of pesticides in fruits and vegetables. And I think there was a big jumping over who first, in the first place, is producing these fruits and vegetables. And the question is the presence of residues in the fruit without going to the farms and thinking about who is there producing that food. So what's unique to the Argentine case is the way in which the agroecology food sovereignty movement came to be. And the question about what strategies are being done to deal with this, the question is about structural racism operating in the institutions regulating all these processes. And so this is a huge question that, and I see people, and here I'm teaching this class, Food Matters, and I ask my students we're analyzing farmers markets, who go to farmers markets to purchase food and who you see there and who are not present in these spaces. And so I see these conversations happening. We are aware that some people have access to healthy food and not others. And so the answer of what are the strategies to manage that is like all these Black Lives Matter movement. So it's a problem of structures. At the core of the problem is racism and whiteness and white privilege normalizing certain practices. Hopefully that answers your question.
Thanks a whole lot, Daniela. And we are witnessing the beauty of Geography Live with two very different talks, and both of them fascinating. Yeah. Milan is asking another question of Tasha. Before I ask that, I want to thank everyone who was tuning in. Again, my apologies for this duplication of links on YouTube. I need to go to a YouTube school. Thanks for tuning in if you need to go. If not, I will be asking one last question from Tasha here while thanking the both speakers. Tasha, Milan's asking, how far can you get with sea surface temperature from satellite by no depth buoy time series in Glacier Fjord? Just snapshots from a few temperature depth transects. And they're saying this is Ethan Welty thinking about Columbia Glacier. Sorry, I get the name wrong there. Yeah.
So the thanks for that question, Ethan. The work that I'm doing is most likely generalizable to many locations for understanding upper ocean temperatures. So I'm doing this in Antarctica. You can do this at Columbia Glacier, most likely. It's only going to reflect, the sea surface temperatures are only going to reflect how the depth at which that water is kind of homogeneous. So along the coast in Greenland, down to 150 meters, in that trough region, it's great because you have warm water at the surface there. So the oceanography is really, really important, but if you have a few snapshots, you can get kind of an idea of what sea surface temperatures can tell you. There's also the option, these plumes come up at the surface, and what we found at Helheim Glacier is that water column throughout that plume is homogeneous. in front of Helheim Glacier, it's 4 degrees from the surface down to depth, which is the Atlantic water is 4 degrees. So there are options of being able to look at in small locations, knowing the oceanography, to know what the deep water is actually like too. Thank you for that question.
Thank you for the answer. I do not see other questions.
I have a question for Tasha.
Oh, great. Okay.
I wonder if there are any policy recommendations that derive from your research. Any application?
Well, a lot of what the policy applications would be: stop putting carbon dioxide in the atmosphere. There are also a lot of the things that we worry about are local issues. In 2012, there was a massive entire ice sheet melt event, which has not really been seen in history. And what that did is it sent a lot of meltwater down into some of the little towns around Greenland and flooded them entirely. So one of the things that Mike did and that we did when we were there was to talk to the local officials about how we can, predicting that in the future and how we can kind of mitigate that. And so on a local sense, we can talk about policy and, building infrastructure to prepare for this. And, if we start to see sea surface temperatures change and we can start to expect glaciers they all change often at the same time when the ocean is driving this. So being able to predict that ahead of time, we can kind of have a little more foresight in when that might happen. But
thank you.
Yeah, thanks.
So we need to fix climate change and structural racism.
All of it. Yes, I loved your talk. Thank you. That was awesome. I don't think I've actually heard about your research before.
Same, that happens. Thank you for this space then.
Credit goes 100% to Joe Bryan for suggesting this exit talk, as well as other colloquium committee members for organizing this. One last question, Tasha. This is also, I guess, back to salinity. I don't quite understand the question. Does the ocean gradually get less saline? That's
from the melt. So in some locations, it can become less saline. And so one thing that we're worried about is that area around Greenland becomes less saline because of all that melt that's entering there. But in other places around the world, evaporation is something that creates more salty water. The creation of sea ice produces saltier water. So on average, it becomes less saline if you melt all the glaciers, because then you have more fresh water in the ocean. And that's definitely a thing, but it's not super significant. It's relative. So I'm talking about relative temperatures. A degree matters. A small change in salinity matters for ocean circulation.
I see. Larger scale question. All right. And I think that latter part of the question was already answered about the temperature and salinity. I assume that's has to do with evaporation that was just mentioned. Okay, we are way over time, 1:15. Thank you, Tasha. Thank you, Daniela. Thank you, everyone who stayed on. Have a good weekend. Stay safe and well out there. Goodbye.
Thank you.
Bye, Danny.
Thank you, Joe.